Here are some electrical rules of thumb for quick design calculations. Firstly, we will discuss a rule of thumb for cable sizing. For single-phase 60 Hz systems, use 100 amps per inch of conduit diameter, 200 amps per number 12 American wire gauge wire, 250 amps per number 10 American wire gauge wire, and 300 amps per number 8 American wire gauge wire. Secondly, we will discuss a rule of thumb for transformer kilovolt amps. For 480 volt systems, kilovolt amps equals 0.8 times the load in kilowatts. For 208 volt systems, kilovolt amps equals 1.6 times the load in kilowatts. Thirdly, let's explore a rule of thumb for lighting load calculations. For commercial buildings, use 1 watt per square foot. For residential buildings, use 0.5 watts per square foot. Fourthly, we will discuss a rule of thumb for motor load calculations. For induction motors, horsepower equals voltage times full load amps times 0.746 divided by efficiency. For synchronous motors, horsepower equals voltage times full load amps times 0.746 divided by power factor. Fifthly, we will discuss a rule of thumb for panel board size. For single-phase 120/240 volt systems, use 1 amp per square foot of floor area. For three-phase 480/277 volt systems, use 0.5 amps per square foot of floor area. Sixthly, let's look at a rule of thumb for wire gauge selection. For branch circuits, American wire gauge equals kilovolt amps times 10 divided by voltage. For feeder circuits, American wire gauge equals kilovolt amps times 10 divided by voltage times current per phase. Seventhly, we will discuss a rule of thumb for fuse and circuit breaker sizing. For circuits with inductive loads, amps equals rated current times 1 plus power factor. For circuits with resistive loads, amps equals rated current. These rules of thumb provide a simplified approach to various electrical calculations and can be used for quick, conceptual designs. Remember to always consult the National Electrical Code, or NEC, and engineering standards for detailed and accurate calculations. These rules of thumb are meant to provide ballpark figures. For accurate and safe electrical designs, it is always best to consult with a qualified electrical engineer. Let's delve into each of these rules of thumb in more detail. Starting with cable sizing, the rule of thumb for single-phase 60 Hz systems provides a quick estimate of the current carrying capacity of different wire gauges and conduit sizes. This is particularly useful in initial design stages where you need to quickly determine the appropriate size of conductors for a given load. However, it's crucial to remember that this is a simplified approximation. The actual ampacity of a conductor depends on several factors, including the insulation type, ambient temperature, the number of conductors at a conduit, and the specific installation conditions. The NEC provides detailed tables, such as those found in NEC Table 310.15b16, that must be consulted for accurate conductor sizing. These tables take into account the factors mentioned above and provide ampacity values based on specific conditions. Next, let's consider the rule of thumb for transformer kilovolt amps. The formulas kilovolt amps equals 0.8 times the load in kilowatts for 480 volt systems and kilovolt amps equals 1.6 times the load in kilowatts for 208 volt systems offer a quick way to estimate the required transformer size based on the expected load. This is helpful in the early stages of project planning when you need to determine the approximate transformer capacity needed to supply a particular building or system. However, it's essential to understand that this is a simplified calculation. The actual transformer size should be determined based on a detailed load analysis, which considers the connected load, demand factors, and future load growth. Demand factors account for the fact that not all connected loads will operate simultaneously. This analysis should be performed by a qualified electrical engineer to ensure that the transformer is adequately sized to meet the actual load requirements. Moving on to the rule of thumb for lighting load calculations, the guidelines of 1 watt per square foot for commercial buildings and 0.5 watts per square foot for residential buildings provide a rough estimate of the lighting load for a given building area. This can be useful in initial design stages when you need to estimate the overall electrical load of a building. However, the actual lighting load will depend on several factors, including the type of lighting fixtures used, the lighting levels required for different areas, and the building's occupancy. Energy codes and standards such as ASHRAE 90.1 provide detailed requirements for lighting power density, which specify the maximum allowable lighting power per square foot for different building types and occupancies. These requirements must be followed to ensure energy efficiency and compliance with building codes. Now let's examine the rule of thumb for motor load calculations. The formulas horsepower equals voltage times full load amps times 0.746 divided by efficiency for induction motors, and horsepower equals voltage times full load amps times 0.746 divided by power factor for synchronous motors, provide a way to estimate the horsepower of a motor based on its voltage, full load amps, efficiency, and power factor. This can be useful in selecting the appropriate motor for a particular application. However, it's important to note that the actual horsepower of a motor may vary depending on the load it is driving. It is essential to consider the motor's torque requirements and duty cycle when selecting a motor for a specific application. The motor's nameplate data should be consulted for accurate information on its voltage, full load amps, efficiency, and power factor. Next, let's consider the rule of thumb for panel board size. The guidelines of 1 amp per square foot of floor area for single-phase 120/240 volt systems and 0.5 amps per square foot of floor area for 3-phase 480/277 volt systems offer a rough estimate of the panelboard size needed to serve a particular area. This can be helpful in the early stages of design when you need to determine the approximate size of the panelboard. However, the actual panelboard size should be determined based on a detailed load analysis, which considers the connected load, demand factors, and future load growth. The panelboard should be sized to accommodate all the circuits required to serve the area with spare capacity for future expansion. Now, let's examine the rule of thumb for wire gauge selection. The formulas American wire gauge equals kilovolt amps times 10 divided by voltage for branch circuits, and American wire gauge equals kilovolt amps times 10 divided by voltage times current per phase for feeder circuits provide a way to estimate the appropriate wire gauge for branch and feeder circuits. This can be useful in selecting the correct wire size for a given load. However, it's important to note that the actual wire gauge should be determined based on the ampacity requirements of the circuit, as well as the voltage drop limitations. The NEC provides detailed tables that specify the allowable ampacities for different wire gauges based on the installation type and installation conditions. Voltage drop should also be considered, as excessive voltage drop can cause equipment to malfunction. Finally, let's consider the rule of thumb for fuse and circuit breaker sizing. The guidelines amps equals rated current times 1 plus power factor for circuits with inductive loads, and amps equals rated current for circuits with resistive loads provide a way to estimate the appropriate size of fuses and circuit breakers for different types of load. This can be useful in selecting the correct overcurrent protection device for a given circuit. However, it's important to note that the actual fuse or circuit breaker size should be determined based on the ampacity of the circuit conductors, as well as the inrush current of any inductive loads. The overcurrent protection device should be sized to protect the circuit conductors from overload and short circuit conditions, while also allowing the circuit to operate normally without nuisance tripping. In summary, these electrical rules of thumb provide a simplified approach to various electrical calculations and can be used for quick conceptual designs. However, they should not be used as a substitute for detailed engineering calculations in compliance with the NEC and other applicable codes and standards. Always consult with a qualified electrical engineer for accurate and safe electrical designs. These rules of thumb can be invaluable tools for electrical professionals, allowing for rapid estimations and on-the-spot decision-making. However, their limitations must be clearly understood. Relying solely on these rules without considering specific project details and code requirements can lead to unsafe or inefficient designs. Let's consider some additional factors that influence the accuracy and applicability of these rules. Ambient temperature significantly impacts the ampacity of conductors. The NEC requires that conductor ampacities be deaerated when the ambient temperature exceeds 30 degrees Celsius or 86 degrees Fahrenheit. This deaerating accounts for the increased resistance of the conductor at high temperatures, which reduces its ability to dissipate heat. The number of conductors in a raceway or cable also affects ampacity. When multiple current-carrying conductors are installed in close proximity, the heat generated by each conductor can raise the temperature of the surrounding conductors, reducing their ampacity. The NEC provides adjustment factors that must be applied when more than 3 current-carrying conductors are installed in a raceway or cable. Voltage drop is another crucial consideration in electrical design. Excessive voltage drop can cause equipment to malfunction, reduce lighting output, and increase energy consumption. The NEC recommends limiting voltage drop to 3% in branch circuits and 5% in feeder circuits. When selecting wire gauge, it is essential to ensure that the selected conductor size will not result in excessive voltage drop under normal operating conditions. The type of load being served also influences the selection of overcurrent protection devices. Inductive loads, such as motors and transformers, typically draw a high inrush current when they are initially energized. This inrush current can be several times the normal operating current. Overcurrent protection devices must be sized to withstand this inrush current without nuisance tripping. Time delay fuses and inverse time circuit breakers are often used to protect circuits with inductive loads. The available fault current at the point of service entrance must also be considered when selecting overcurrent protection devices. Overcurrent protection devices must have a sufficient interrupting rating to safely interrupt the maximum available fault current. The interrupting rating is the maximum amount of current that the device can safely interrupt without failing. Inadequate interrupting rating can result in equipment damage, fire, and personal injury. The specific application and environment in which the electrical system is installed also influence design decisions. For example, electrical systems installed in hazardous locations, such as those containing flammable gases or dusts, must be designed and installed in accordance with specific requirements to prevent explosions and fires. Electrical systems installed in wet or corrosive environments must be protected from moisture and corrosion. The NEC provides detailed requirements for electrical installations in various types of occupancies and environments. These requirements must be followed to ensure the safety and reliability of the electrical system. In addition to the NEC, other codes and standards may also apply to electrical installations. These may include state and local building codes, energy codes, and industry standards. It is essential to be familiar with all applicable codes and standards when designing and installing electrical systems. Continual learning and professional development are essential for electrical professionals to stay up to date on the latest codes, standards, and technologies. The electrical industry is constantly evolving, with new products and technologies being introduced regularly. By staying informed and continuously expanding their knowledge, electrical professionals can provide their clients with the best possible service and ensure the safety and reliability of electrical systems. In conclusion, while electrical rules of thumb can be helpful tools for quick estimations and conceptual designs, they should not be used as a substitute for detailed engineering calculations and compliance with applicable codes and standards. Always consult with a qualified electrical engineer for accurate and safe electrical designs, considering all relevant factors such as ambient temperature, conductor deaerating, voltage drop, load characteristics, fault current, and environmental conditions. Remember to prioritize safety and compliance in all electrical work.